Hello, I am Idoia Ruiz, co-author of the paper Weakly Supervised Multi-Object Tracking and Segmentation. In this paper, we address the multi-object tracking and segmentation (MOTS) problem for cars and pedestrians. It comprises the tasks of detection, classification, instance segmentation, and tracking. As annotations, we need bounding boxes, pixel-wise masks, and consistent identities along the video sequence. The motivation of this paper is overcoming the difficulty of getting these expensive annotations. Therefore, what we propose is to solve the MOTS problem without using any mask annotation, the most expensive kind, either from the target dataset or others. We train our model in such weakly supervised setting. The novelty of this work is then to define the problem of weakly supervised mods, that is, multi-object tracking plus weakly supervised instance segmentation, and address it for the first time. As the base model, we use Modsnet, an architecture that was introduced in our former paper. We have added to Modsnet two one-by-one convolutional layers in the classification and detection branch of the region segmentation head. This is needed in order to extract activation heat maps, as I will explain later. Essentially, the MODS architecture is a masker CNN with a ResNet50 backbone with an additional tracking head that learns an embedding to associate the objects in order to build the tracks. To train Modsnet, we use a loss that is the linear combination of losses of the modules it is composed by. The total loss is the combination of the tracking loss, the region proposal head loss, and the region segmentation head loss, with a regularization parameter lambda. The region segmentation heads learns the tasks of classifying, detecting, and generating pixel-wise masks for each object instance. Each task is learned via its corresponding loss. In the fully supervised case, the instance segmentation branch is trained by using the ground truth masks with a cross-entropy loss. This is the loss for classification, detection, and instance segmentation. But how do we do it for the weakly supervised case, in which the mask ground truth is not available? We propose the combination of the following three losses: the foreground localization loss that learns what is foreground and what is background, the CRF loss that retrieves the edges of the objects, and the tracking loss that provides extra supervision from tracking. I will introduce them individually in the following slides. Then, this is the loss in the weakly supervised setting, the combination of the foreground localization loss and the CRF loss. Let's start with the foreground localization loss. It uses activation information that looks like this, transformed to pseudo-labels to learn from. We have added two one-by-one convolutional layers in order to extract such activation information. The activation information is computed by using RADCAM. Basically, it combines gradient plus activation information from the last convolutional layers, those that we have added before. This provides localization maps that look like the images on the right side. In particular, the gradients weight the activation maps. In the original implementation, the authors only considered positive combinations of activations and gradients by applying a ReLU operation. Instead of using the original RADCAM formulation, we propose the following modification. We have found out that using both negative and positive values by taking the absolute value of alpha leads to maps more suitable for being used as a pseudo-label, as it covers a broader area. The reason behind is that negative gradients of high magnitude can also be meaningful for instance segmentation tasks. Now, how do we use these RADCAM heat maps on the foreground localization loss? We do it as follows. The bounding box ground truth is available. Then we can be sure about what's outside these bounding boxes is background. We are not so sure, however, about what is inside them. Then we threshold the heat maps, so that what is above a certain threshold will be learned as foreground, while the pixels inside the ground truth bounding boxes, which heat map values are below the threshold, will not contribute to the loss. The blue box here represents a possible candidate bounding box, while the green bounding box is a grounded bounding box. Then we consider the blue shaded area as background and the red part, that is the heat map part, which is above the threshold, we consider it as foreground, and we learn from this. This way our model learns to model background and also small part of the foreground. This will be the composition of the pseudo-labels we create for pedestrians for this frame. The foreground localization laws is then a cross-entropy laws that uses the generated pseudo-label as the true label. The objective of these laws is to learn what is foreground and background for the instant segmentation mask. These are examples of the pseudo-label generated from Gradient heat maps and the predicted masks by the network. But how do we retrieve the boundaries of the objects? Because by now we only have weak localization information. For that purpose, we have added the CRF laws, which was introduced in the cited paper below. Please check the details in the original paper. Basically, what it does is to propose a relaxation of the POTS model, introducing a law that tries to learn the same effect of applying the CRF regularizers. In practice, this recovers the edges of the objects and enforces consistent and homogeneous masks. Finally, there is a final contribution to the weakly supervised learning intrinsic to Modsnet, as the tracking branch contains a Masspooling layer, which was introduced in our former paper. What Masspooling essentially does is to only consider the foreground pixels of the object to predict the features employed for the tracking association. This way, the foreground object is better modeled and so are consequently the tracking features. This is useful, for instance, when the object foreground does not cover most of the bounding box area. Of course, for Masspooling, we use the predicted mask, not the grounded ones, which are not available. That is what we will do in the fully supervised case. The tracking head at inference time just predicts embedding vectors to associate the predicted objects in the frame to those of the rest of the frames of the sequence in order to build a tracklet. But at training time, we optimize a hard triplet loss to train the tracking head, so that in the embedding space, we push together objects of the same identity and we push away objects of different identities. Then the tracking task is indirectly supervising distance segmentation as the gradients are backpropagated. Now let's see some results. We have employed the most popular benchmark for mods, Kitty mods, as it is a recently introduced problem and there are not many. For evaluation, we use the official mods metrics defined below. Mods A and Mods A assess detection, tracking, and segmentation quality, while Mods B measures the segmentation quality isolatedly. In the top of the table, we show the results of our method under a fully supervised setting, compared to the state-of-the-art under the same pre-training conditions, that is, only pre-training the ResNet backbone on ImageNet, but not any other component of Masker CNN. In the middle, we report the performance when we do not use any kind of instant segmentation masks. The bottom row shows the relative performance drop, which in the case of Mods P, the metric that measures the segmentation quality isolatedly, it is just around 12%. We do not perform so well in other metrics, probably because we need more hyperparameter optimization. Although many parts of Modsnet are the same, there exist some differences, like the different tracking post-processing and the two added one-by-one convolutional layers. Finally, we have conducted an ablation study to evaluate how important are the different losses that contribute to the supervision of instant segmentation. So, the first row is what we get when using the supervision of the three losses, and we have tested what happens when we remove one of them, using exactly the same hyperparameters. Of course, the foreground localization loss is necessary, otherwise it just does not learn at all. That is why this variant is not considered in the table. When we remove the CRF loss, the performance significantly drops, because this loss is needed to predict the edges of the objects. To remove the supervision of the tracking laws, we still train the tracking head, but we do not propagate the gradients to the instance segmentation head. It turns out that tracking helps with pedestrians, but not so much with cars. However, pedestrians are the hardest class in our case, so it is useful as long as it improves the performance on the hardest class. In summary, the contributions of this work are the following. We define the weakly supervised mods problem as joint weakly supervised instance segmentation and multi-object tracking, and propose the first approach to solve this challenging task. We designed a novel training strategy by taking advantage of the multitask problem. The different branches of our architecture, that is Mass-Gaussian and Bayes, are trained in a synergistic manner so that the supervised classification and tracking tasks guide the learning of the unsupervised one, that is instance segmentation. We compare our method to the fully supervised baseline on the Kitty Mods dataset, showing that the drop of performance on the Mods P metric that evaluates instance segmentation quality is just at 12 and at 12.7% for cars and pedestrians respectively. Finally, we provide an ablation study about the contribution of the components of our approach. Thank you very much for listening.